Hi and welcome to TRX Bench. I got some requests if I could explain a little bit about the IP3TX product, which is the intermodulation on transmit, and how can we measure it, and what is it all about. So yeah, that is what we are gonna do today. I want to show the procedure, how to measure it step by step, and yeah, we want to look a little bit into this issue and why it is so important, and why a high intermodulation product really could produce some distortion on air. So let us go right to the bench and go really step by step to understand how it works. And of course, when we talk about intermodulation, we need to know what PEP power is, and we need to understand how it comes together. And therefore I can highly recommend to watch my video number 42. So this is all about PEP power, and that might be helpful to understand a little bit more what we are doing when we are measuring the PEP power and the intermodulation products. Okay, and so let us first see what the service manual is telling us. Okay, and this here are the specs, and yeah, let me enlarge it here a little bit. And when it comes here to transmitter, we find here that we have a spec for third order intermodulation, and it is telling us minus 31 dB at 14 megahertz and 100 watt PEP, and yeah, there it is. So the spec is telling us that we should test the intermodulation product with full power, because this radio here is a Yaesu FT950, so that is a 100 watt PEP radio, and the specs are telling us that with full power on 14 megahertz, this radio should produce not more than 31 dB intermodulation, or let me better say it, the intermodulation products should not be worse than minus 31. Okay? And you see, I have already dialed in 14 megahertz, and the radio is set, of course, to SSB, in this case to upper sideband. And now it is important to adjust our passband filter to the right filter width, and that can be done here. And you see I'm able to adjust my filter width, so it is indicated here. And normally we will test our filter, we will test the intermodulation products with a filter width of 2.7 kilohertz, because that is the normal filter width which we are using on SSB. And of course, if we are talking about single sideband, we need test tones, audio tones, which we need to feed into our transceiver to get these tones transmitted. And therefore we need test tones in the audio range. Okay? And of course, most of you will have already heard that intermodulation products on SSB can only be tested with a double tone, and therefore I'm using here my little generator, and this generator has two outputs, so I have a channel 1 and a channel 2, and I have already prepared here my settings as I'm usually using it. And as I already said, we need audio tones, so in the audio speech frequency range, yeah, we all know that these audio tones will be converted in the radio to a HF, RF tone, or RF fundamental, whatever we want to call it, and that is then, of course, in the frequency range where we have the radio dialed to. So in our case it is of course dialed to 14 megahertz, and then our audio tone, which we will dial in here in this frequency generator, will be then mixed onto our carrier tone. Let me call it like that. Also, we all know that with an SSB transmission we do not have a real carrier. So SSB is with suppressed carrier. So that is for sure, but we will have at least two tones which will be in the 14 megahertz range in our example, because the specs are telling us we should test the intermodulation products with 14 megahertz. And I'm using two tones, and you can already see it here on the display. So I'm using 1.44 kilohertz, and the second one, which is here on my second output, and that is 1.96 kilohertz. So this both frequencies are in a distance or a delta of 520 hertz, and that will be important later on. But you see, yeah, I have both frequencies already dialed in, and what I have done as well, I set my amplitude for both outputs to 16 millivolt peak, so that is for both output right at the start the same. That might be adjusted a little bit, but we will see it when we go ahead. And of course we need now to mix this both frequencies together, that we have at least our double tone available at our microphone input. Well, I'm using here this little combiner, and this combiner is by far nothing special. I have just two 100 kilo ohm resistors here in let me see, in this little combiner here. So just like this, it is really simple, nothing special, and therefore yeah, we are here in the audio range, and that is not really critical. So I have here now our output, and when I engage both channels, then I have here at the output my double tone available. Right, and I have here my alligator clips, and I know this radio here has right in the middle the microphone input, so I can connect my red alligator which is carrying our double tone. I can connect directly my alligator here to the middle of my mic connector, and I put the ground here to you know, this ground, which is not completely right, because in this radio we have a pin which is really available for handling our audio ground. So there is a little coil in between, but okay, I don't use it because I do not want to short here some pins together. And let us check if we can get the right intermodulation product, even if we use this ground here at the outside of my connector. So that means the little coil which is normally in between is now not there, not present. Okay, so then the next preparations are, so we just have to set our mic gain here to maximum a quarter, so that the mic amplification is very little, and you have to switch off your mic processor, so that is what you do not want, and the mic equalizer should be switched off as well, as far it is available in your radio. But well, all newer radios do have an internal equalizer, which is here indicated with this light, and if I press it twice, then you see up here that the processor is engaged as well, and I do not want to have this features engaged. So the only thing I want to have is my normal mic amplifier, and I start off with setting it to a quarter, and the second I want to adjust is my power, and yeah, you can see it down there. Let me see. So here I'm able to adjust my power, right? And I will start off with 5 watt, because we first of all need to adjust our radio, our tones to a level that we really can start off, and therefore I start here with a very little power amplification, and it is only set to 5 watt, just to adjust the rest of our setting here. Okay, and before we go into our spectrum analyzer settings, let us have a look to this little picture, and yeah, that will illustrate what we are doing. So this here is our frequency axis, and this here, of course, our power axis, right? So we have already set the radio to 14 megahertz, as we have seen it in our technical specs from Yaesu, right? This here is representing our 14 megahertz, and we know on SSB we do not have at least a carrier, so the carrier is completely suppressed, and what we have is our high frequency tone, our high frequency component, and this is, of course, because we have added our audio tone is now added to our HF component. And of course, if we have the radio set to 14 megahertz, then of course our first tone here is 14 megahertz plus our audio tone, which is the first one, or the lower one is, as we dialed it in to our generator, our audio generator, is 1.44 kilohertz, and that means of course that this tone here is 14 megahertz plus 1.44 kilohertz, right? And this tone here is of course 14 megahertz plus 1.96 kilohertz, and this is now, or these are now our both tones, our double tone. And as you might remember, as we are talking about single sideband transmission, we do not want to see our lower sideband, which would be below 14 megahertz, and therefore we have a filter set here over this range. And of course it is not set here in the radio behind the last stage, because we can change the band and the frequency and what have we, and we only have one SSB filter, and that is very much at the beginning, at the front F, and right behind our microphone amplifier, and of course it is directly behind our SSB balanced modulator, because there we have one frequency for all the different bands, because the mixing will be behind that portion of our complete SSB circuitry. Yeah, and we have seen it here already. I can adjust here my filter width, and we all know, as I already said, the normal filter width of a SSB filter is 2.7 kilohertz, and you see I can adjust it to a smaller width and a greater width, so whatever you want to have it, but normally it is around 2.7 kilohertz, and that is the reason why I have set now the filter in here to 2.7 kilohertz. So this is a DSP radio, so therefore I'm able to adjust it via software. Normally you would have a fixed filter, maybe a good Collins filter or Sherwood filter or whatever inside your radio, so that is then a crystal based filter or what have we. So in this case it is DSP operated, and therefore I can set here my filter width to 2.7 kilohertz. Yeah, and back to this little drawing here. I know it is not fancy, but I hope you understand what I want to show you. So the filter width of 2.7 kilohertz is showing here with the red line. So that is at least our SSB filter, and the filter width here from the start to the 3 dB point at the end of this filter is 2.7 kilohertz, and that means our complete voice, all what we do over band on SSB will be within this filter width, right? And therefore, of course, our tones here needs to be within this filter width, right? Okay, and I've done already all the settings we need, And what you can see here, that our center frequency is 14 megahertz. So that means if we would have, like on AM or maybe on FM, if we would have a carrier, we would see here our tone. If we would push the PTT as dead key, so without modulation, we would see here then in the middle, right in the middle, our 14 megahertz tone. So that is then the carrier. Now we are working on SSB, so that means our 14 megahertz tone is suppressed as much as possible. And that happens, of course, in the balanced modulator. So you can watch, if you like, my video number 66, where I explain how the balanced modulator is working and how the carrier will be suppressed. So there you get all the informations about that. So that means as long this is 14 megahertz and we are working on upper sideband, that means our tones will be here right beneath our center frequency, right? So as we are talking about the audio bandwidth of 2.7 kilohertz, that means that all the tones here should be visible here in this area. And you may have already seen that I have set the span here to 10 kilohertz. I hope you really can read it here. I can't really see it through my camera, but that may be because it is only this little LCD display. I hope you really can read it here. Okay, so the span is 10 kilohertz, and that means we have 10 divisions here, and if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so that means with a span of 10 kilohertz, so we can look from here to there, from 13995 to 14005 megahertz, and you see that this is 10 kilohertz. So we can really see from here to here in a bandwidth of 10 kilohertz, and that means we shouldn't see anything here below our imaginary carrier, but we should see our tones here right beneath our imaginary carrier, which is of course suppressed. Right, and that can be seen here. So our center frequency is 14 megahertz and our span is 10 kilohertz, and that is what I've set here before, and I have set here my ref level to 55 dBm. So why 55 dBm? So very simple, 50 dBm is 100 watt, and as long our radio should produce, as we find it in the spec, 100 watt output power on SSB, we of course want to set here our reference, and the reference level is then here, the upper line is set to 55 dBm. So you can see see here. Yeah, all right, this is the upper line, and you can already see here 35, 45, 55. And once again, 100 watt will be 50 dBm. All right? And of course, you cannot give your full output power from your transceiver to your spectrum analyzer. You would simply kill your spectrum analyzer with a power like 50 dBm, 100 watt, so don't do it. I have, of course, attenuators in between, and I have a big power attenuator in between with 40 dB, right? And I have a little attenuator right in front of the input of 10. So that means altogether I have 50 dB attenuation in between, and that is set into this field here. You see that I have ref offset, and I have set my offset, of course, because I have 50 dBm, not dBm, sorry, 50 dB attenuation in between. I've set it here to 50 dB, of course, right? So, and now I don't need to be scared, because I can now feed the signal here into my spectrum analyzer right here. So this wire here is coming from my attenuator, and I've here the little attenuator of 10 dB in between as well. So I really have 50 dB in line, and that means the 100 watt coming from my transceiver will be at least present here at the input with 0 dBm. But as I have set my reference offset, the picture here, so the display, will report the right output level coming from our radio. Okay? Okay, so then let's start with our first tone. So when I now engage my signal generator, I'm interested to adjust my output tone here on our spectrum screen to a level of 44 dBm. Why 44? So that is 50 dBm minus 6 dBm, and that is then 44 dBm. And 44 dBm represents an output power of 25 watt for a single tone. Okay? Alright, so let me switch on my first tone, and you see what I have. And yeah, let me put a marker onto my tone here. Should be here. Okay, and what you can see right here in the bottom, so this tone here is 14001439, and remember what we have dialed in here at our generator is an audio tone of 1.44 kilohertz. And as I explained it before, what you can see here right now is that this 1.44 kilohertz is now added to our high frequency carrier tone, whatever you want to call it. But what you can see as well, for the moment in time, we have an output of 21 dBm. And as I said before, I want to set the output level for a single tone, first of all, to 25 watt. And 25 watt is 44 dBm. So 50 minus 6 is 25, right? Very easy. 3 dB means always half the power, and that means 100 watt minus 3 dB would be 50, and minus 6 dB is twice 3 dB, means it is 25 watt. And therefore I will now increase my output level from my radio, right? Remember, my radio is set to the lowest setting ever possible, and the mic gain is set to 1/4, and I go now and increase here my TX output level. Okay, so first of all I set my TX output power approximately to 40 watt, right? But as you can see, we have not finally reached our 44 dB, what we want to reach, and you can also see it down here. So that is representing 10 watt for the moment in time. So that means I do not want to increase my TX output power, so you always have to play a little bit with the dials and the pot. So I will now increase very gentle my mic amplifier, and yeah, and you see, oh yeah, and you see I'm already on 46, which is too much, and now I'm very close to what I want to have. So you can see it here. This tone here is now at 25.2, so maybe we can reduce it just a little bit, but this is now yeah, now we have 25 watt, and you can see it here, very nice. So this is my first tone adjusted to the right level of 25 watt, and that is what I want to do with my second tone as well. Okay, so the fan is already switched on, so the radio is on stress. So now I switch on my second tone on 1.96 kilohertz, and I switch on the transmitter, and here we have our output signal, and I will place now my peak up to there, and you see the power for this here is a little bit too high, and now I can't reduce this power with my radio controls, because if I would now change my mic gain or my TX output power, I would directly reduce my tone on 1.44 kilohertz as well, and you see my second tone on 1.96 is already a bit too high, and you can see it there as well. So what I need to do right now is to reduce my output power here with my controls. So I need to change it maybe here, and I now would yeah, can you see it? I hope I would now reduce it here to bring it finally on 25 watt. So let me show it here, and the impact will be, now I'm turning it down, and you see here, you see the change, and this is now a bit too less, Now we are on 22.8 watt, so I need to adjust it here very little, and you may better see it here, right? So I really need to adjust it here very carefully, and you see here it seems to be now in a good shape. Alright, and the question may already be why I'm doing this here so precise. So what are you doing here? So, and that is because both tones needs to be exactly on the same level, because we only can do a proper intermodulation test if both tones, and I will switch the second tone on in a second, then it is absolutely crucial to have both on the same level, because only then it is possible to measure the right intermodulation product third order. Okay? Okay, so let me now switch on both tones, and here we are, and you see that first of all it is not any longer 44 dBm, because the setting we have done before was for one tone. Now we have two tones, and you already see that we have here some odd products, what we want to talk about a bit later. But what we already can say, that the power density in our transmission channel has now changed. So we have not our 44 dBm present for both. But that was not the purpose. The purpose of our alignment was that we nearly get the same output level. As I already said, this both tones really needs to be on the same output level, and that is what we have already here. And to get now this both levels back to 44 dBm, we need of course to increase our output power, and that is what we are doing here. So I'm really pushing here for 44 dBm. So that is what I'm trying to achieve, and now you see both tones are already now on 44 dBm. Yeah, with a little delta, but that is not too bad right now. Well, and now you see we have of course our 44 dBm for each of our tones, but you see here, so that is really horrible what we can see here. So there are so many intermodulation products that you really can't believe it. So something must wrong. And you may remember I said that I'm gonna use this outer ground, which is not our real mic ground, because as I already told you, there is normally a coil in between when we connect our microphone here to the right jack and or to the right pin, and the pin here right in this upper place here, this is really our mic ground. And is it possible that this little coil will have really an impact on our odd spectrum we have seen. Okay, so let's try once again. I switch it back to transmit, and you see 44 dBm is right, but all these components. So I pull off my ground and I try to bring it to the right position here, which is somewhere, yeah, so that is me, but it is this here, and aha, so now it looks much better. So oh, that means you really need to be careful with what you are doing, right? Alright, so now it is connected to the right mic ground, and let's see how it looks like. Okay, so let's switch back on, and aha, so that is definitely much better. Okay, so now we have our both tones, which are at yeah, if we go to our power meter, you see suddenly I'm measuring here average power. Okay, so what you see is that the average power is now above 50 watt. So that means that we have at least too much power overall. But the question here is, why is it so? I mean, we set our tones to 44 dBm, right? And that is what we see. I mean, it's a bit too much, and that is what we will reduce a little bit. But finally, we see both tones are approximately on here our 44 dBm, but on our power meter we have seen the power is above 50 watt on average. Okay, on average. So so what is that? I mean, 44 dBm is 25 watt, so that is what we have heard before. But now we have two tones here in our passband, and we have two tones of 25 watt average for a single tone power. So 2 times 25 watt means 50 watt, and that is the reason why we can read on our power meter a power which is exceeding the 50 watt, because now these both fundamentals, these both tones are added together to 50 watt. So that is now the power density here in our channel, if we want to call it channel. I mean, it is just to understand it a little bit better. And if we would now test or measure our channel power, we would see it is really something around our 50 watt, what we have seen on our power meter. Okay, and we have seen that we have now too much power, and we want to reduce it, that we have at least our 50 watt, and that is what we can see now here, jumping so a little bit more maybe, but now you see it is in average. So that is important to know. So here is really taken an average sample, and now we are approximately on 50 watt output power. Okay, and once again we are here on our two tones, which are now transmitting in this, yeah, I've called it channel. It is not a channel, we all know that, but to make it a little bit more yeah, visible what we are talking about, we see that this both 44 dBm components are together 50 watt in the channel, because both components are added to 50 watt. But I mean, we are always talking about a radio with you know, 100 watt PEP, and yeah, we are testing here in the moment in time average, and we need to test PEP, and that is now PEP what you can see here. And now you see our 100 watt output power on PEP. I mean, I have nothing changed than what we already had before. It is just the difference between average and here our PEP. And yeah, okay, that is now the question how, oops, this hangs together. And I can highly recommend you to watch my video number 42, where you get all the informations on, finally, you get all the informations on PEP power and how it hangs all together. Well, and this picture here, before we go ahead to understand what we all can see. I mean, we are interested, of course, in the third order products, but we have seen there are much more to be seen on our spectrum. And this here are, of course, our third order products, but as you can see, there are also fifth order products, there are second order products, and of course, there are spheres and harmonics as well present. So we have really many different components which are all in our passband, and this is, or this happens in our transceiver, because our third or fifth or second order products are not real. They all are artificial. I mean, our radio adds these artificial components to the complete frequency content, right? And therefore we have really a lot of different components in our passband. Important for us, our our third order products are available in this order here: 2 times F2, which is the right one, minus F1. And if we calculate that, we will find that the delta between a fundamental and our third order product is always 520 Hertz. So just easily take the components which we have. Yeah, we need to get it here for a second, and you see up here the fundamentals, and I have already placed here a marker, so you can't see now the second fundamental, but following this little mass here, that the third order product is 2 times F2 minus F1, or the lower one is 2 times F1 minus F2. And once again, if you are calculated with our values, you find that the third order product is 520 20 Hertz away from our fundamental. Okay? Yeah, and when we watch this here, you already see that I've placed here on this component a marker, and our marker 2 has a delta from this fundamental of approximately 520 Hertz, and that is absolutely the delta which would be found if you do the little mass we have talked about. So this little mass, because we are now checking this third order product, and once again 2 times F2 minus F1, and then you find your component here 520 Hertz away from the fundamental. So that is the delta. So that definitely means that this here is our third order component. And on the other hand, if we would like to see our second one, which is most probably this one here, and you see that this is not equal. So that is, maybe there is a little misalignment here in the radio, or maybe there is something with a mixer, so that there is something not 100% in balance. So you see that is not what we would expect, because normally we would see these third order products on the same level. And even so, you see that here our fifth order product, once again, have a look. So this here is our fifth order product, and even that should be smaller than, of course, the third order product. And we find it here, it is more or less, it is even worse. And that is something, if we key here our transmitter, so this may be due to the fact that we have here an overdriven mic amplifier or such, or so this is what the changing, what you can see here is nothing else but here my ALC, and that changes when I change here my mic amplifier. And of course, when I'm transmitting with 100 watt output power, I should really not overdrive my ALC here. And if you do so, you will really change your output components. So therefore it is always something you need to consider when you are performing something like this here, because you can simply get wrong measurements if you do not really take all these different impacts into consideration, right? Okay, and that is now the spectrum of let me call it, I've pushed all to the limit. So the radio is really transmitting with 100 watt PEP, and the ALC is at its limit, so it is not overdriven. So everything is pushed to the limits, and I have put both delta markers here to our both third order component. And what you can find here, so this here is at minus 30.2 dB, and that is always calculated here from our fundamental, and this one here is minus 35.9, so that is almost minus 36 dBc from the carrier, of course. So that is now the final output spectrum, and yeah, we see here a little difference. So what you always need to do, you need to play with your ALC, you need to play with your output power, you need to look that these both fundamentals are on an even level, so that is absolutely important. And then you can finally check your third order components. And well, we have seen in our technical specs from Yaesu that with 100 watt PEP, this radio should be able to deliver a third order product which is not worse than let me double check. I have it here, so which is better than minus 31 dB. So that means if we see here our second third order product, this is only minus 30. I mean, this is even better, so no problem with this one, but the second one here is out of limit. But now it is a little bit critical, because what we are checking here is from the fundamental, but we know that the fundamental here is at 44 dBm, so it is 6 dB under 50, so 6 dB under 100 watt. And if you want to check it from, you know, 50 dBm line, so that means that you really have to go up to 50 dBm, and that means we have to add to this, and this of course as well, we have to add our 6 dBm, and that means this component here calculated on the SSB PEP output level would then be minus 36.207, and that means this radio is really in spec, very good in spec, because Yaesu is telling us that they want to see at minimum 31 dBc, so under this carrier, and calculated here on this average components, it is 30.2, but they are telling us that it is on 100 watt PEP. And once again, if we want to calculate it on PEP, we have to add our 6 dB, which is not present here, so therefore it is 36.207 calculated on the PEP level. Well, but sometimes it is not really clear what the manufacturer means with this third order EMD product, so sometimes it is really calculated from the fundamentals, but if you want to do it right, you really have to do it from 50, and that means you have to add this 6. But I have just adjusted a little bit the fundamentals by changing our input here from our generator, and that then, because I made it here more equal, and now you see even from the fundamental we are reaching this minus 31 dB. So even if Yaesu means it from this perspective, it is in spec, and it is more than in spec if we calculate it from our 100 watt dB 100 watt output level calculated plus 6 dB. So that means this radio is in spec, and yeah, now let us talk just a little bit about why these components are so critical. Well, and I don't really want to drag it out too long, so just briefly, why is it so important that our intermodulations products are not too huge? So that's very easy. If we see here our passband, and we see here our double tone. So the double tone, or if you like, what we are talking while we transmit, that is what we want to transmit. And what we want to see is only the fundamentals, and we don't want to have anything additional to what we are really giving into the system, right? Well, but when you see this here, right, you simply see that there is a lot of content which is not present right from the beginning. So when we talk into the radio, we only have our normal audio frequency, and then we get here a lot of odd components into our transmission band, and that is something we definitely do not want. And again, why is it so critical, our third order products? Well, very simple. Remember, this is here in our passband. Yeah, and that is what it is. So we have here our SSB filter, and we have here our filter, bandwidth, and the third order products, and maybe as well the fifth order are here in our passband, and we are not able to simply eliminate these components with a filter or such. I mean, we can reduce harmonics with our filtering at the output. So that is no problem, because, you know, a harmonic is far away from the carrier or from the fundamental. But these third order products are right in your transmission channel, and that means they can be heard if they are too big. And you definitely have heard it on the band already. So there is splattering and such. And that is because these products are getting too high that they really get heard on the band. And that is a problem. There is nothing how you can reduce it then. Do your settings at the radio probably, so just don't overdrive your amplifier, don't overdrive your microphone amplifier, take care on your ALC, and then you can be sure that the third and fifth order products and what have you are reduced to a point where they are not harmful. And therefore, this is the reason why you always have to have this on mind, because you really get a white signal and you are splattering, and that is what we want to avoid. And therefore we need two things. First of all, you need the proper setting, and you are responsible for your setting. And secondly, we of course need a radio which is able to really delivers figures like this, because the absolutely minimum you ever need is 20 dB intermodulation, third order intermodulation. So that is the minimum. So that means, on the other hand, that this component could be sit here at this line, but that is then really the absolutely maximum whatever should be possible on the band. Okay, and yeah, I just have set up this here once again, and I've placed here one marker, and now I'm increasing the mic gain, and what you see is that suddenly you can see it here. Yeah, we only have 11 dB intermodulation. Yeah, so that means now the radio is completely overdriven. And you see it here, the ALC is max too high, so we really should reduce it to that point here, and then our intermodulations product are back normal, so without any problem. But if we push it here like hell, it is clear that here, so this is incredible, and you may understand that these components can be heard on the air, and this here will produce splatter for sure. And just shortly, where does this artificial tones come from? I mean, these are mixing products which always happens when two signals get mixed, and an active component like a diode or a transistor or what have we, because all these components do not have a linear characteristic, and always when there is a component involved which does not have a completely linear characteristic, then you get mixing products, and mixing products are always artificial tones, and that is what we can see here, and that is what we need to avoid. Alright, so that's it. It is already not a short video. Well, okay, but anyways, thanks for watching. Hope you enjoyed it a little bit, and if just give me a thumb up, and yeah, catch you next time. Bye.